Hi, good morning, everyone. Yes, this is Mr. Chua speaking, class 402 of year 2020. Yes, I'm addressing to you guys right now. Well, I'm not able to make it to school today, but not to worry. We shall continue to have our AMAS lesson, where I'll be teaching some of the new stuff to you guys through this video. Okay, at some point in time in this video, I will actually invite the relief teacher to pause the video so that you guys can have some buffer time to jot down what has been gone through. But before we start, give you guys a quick 10 seconds to quickly take out all the items that you need for this lesson. That means you need to have your textbook, your exercise book, and your writing materials, of course. 5, 4, 3, 2, 1. All right, so I hope you guys have the relevant materials with you on the table, and we shall start our lesson. Okay, in case you've forgotten, we actually completed chapter 15 on the excruciating connected rates of change, which some of us seem to be struggling with. And just for the record, I have not collected the homework from you guys as well. So, Kanes, can you please collect the homework, arrange them in register number, and drop them in my locker number 40. Please hand in by today. All right, so back to the focus for today. Today we're gonna enter chapter 16, where what we're gonna learn. Now, first up, as you can see on the right-hand column here, we're gonna talk about what a stationary point is. Okay, I've actually briefly mentioned in class before, but I'm gonna go through again today. Then next time, I'm gonna walk you guys through the different types of stationary points that we have. And last but not least, I'm going to teach you guys on how to test for the nature of the stationary point, or what I've written there, turning point. At this point in time, if you do not understand what I just said for pointer number 3, not to worry. Okay, you'll know it when we are there. Okay, so let us start lesson proper. First of all, a very quick recap. Oh, okay, gosh, I can't even spell recap correctly here. Okay, a very quick recap. Ladies and gentlemen, can you remember why do we have dy dx, or why do we find dy dx? Yes, dy dx gives us the gradient of the tangent to the curve. Okay, so say for example, I have a curve here. And I want to find out what is the gradient of this point. I'll draw a tangent line, and of course dy dx gives us the theoretical value of the gradient of this line. So I also mentioned before, but just a quick recap, at stationary point. Okay, what happens at a stationary point? What is the value of dy dx at the stationary point? Okay, the value of dy dx at the stationary point is actually equals to 0. That means to say, if you think about it, what kind of tangent line do we have here? Yes, we are talking about a horizontal tangent line here, where the gradient of this tangent line, of this horizontal line, is equals to 0. Now, at this juncture, I'd like you guys to think through when do we have a horizontal tangent line? A quick 10 seconds, you may discuss with your partners. All right, yes, you are right. We are probably looking at the instance where we have a minimum point. Because what happens at a minimum point is where when I draw a tangent to the curve at a minimum point, I get a horizontal line where dy dx equals to 0. Likewise, you guys might probably have thought of this as well, is when I have a maximum point where my dy dx is equals to 0. Again, the gradient of this tangent line is equals to 0, hence explains why I have a horizontal line. Okay, maximum points. And actually a third one which we haven't really discussed is when I have a point of inflection. Okay, let me just draw this properly. Okay, is where I have this point of inflection here where I get a horizontal line as well. So there you have it, ladies and gentlemen. That address point number 2, where these are the 3 different types of stationary points that we are talking about: a minimum point, a maximum point, or a point of inflection, where we have the stationary point that gives us dy dx equals to 0. Okay, so at this point in time, can the relief teacher please pause the video to allow our students to jot down this? All right, so with that in mind, let us try to apply the knowledge of stationary point on the question. So example number 1. Now find the coordinates of the stationary point for the curve y equals to x cubed. All right, so first of all, you're supposed to find what's the coordinates of the stationary point. And as we have just discussed, stationary point is when dy over dx is equals to 0. So the first thing I got to do is I need to go and find out what is dy over dx, which I believe is no kick for all of us here. This is just 3x squared. Okay, so what happens at the stationary point? My dy dx will be equals to 0. So from here, I can actually find out the value of x, which is x equals to 0. So of course, we are supposed to find the coordinates. X equals to 0 is just part of the answer. We need to find out what is the y coordinate as well. So at x equals to 0, y is equals to 3 times z, sorry, not, it should be y equals to 3 times 0 cubed, which gives us 0 as well. So ladies and gentlemen, our answer here, coordinates of the stationary point is 0, 0. Simple as that. In fact, without finding, for some of us who are familiar with the graph of y equals to x cubed, you would have been able to tell me that this is actually the shape of y equals to x cubed graph. All right, so you'll notice that this is actually my point of inflection at 0, 0, where my dy dx is equals to 0. All right, so can I invite the relief teacher to pause this video for a short while so that our students can finish up what I've just written. Thank you. All right, so I want to talk about this next example here, where we are asked to find the coordinates of the minimum point for y equals to x squared minus 7x plus 2. Okay, so if you guys can recall, when it comes to finding coordinates of the minimum points for a quadratic curve in EMAS, what are the different ways that I can help us determine the coordinates of this minimum point? Take a quick 10 seconds to discuss with your partner. 5, 4, 3, 2, 1. Yes. All right, if you're familiar in EMAS, to find the coordinates of turning point, there are actually 2 methods. First method is, of course, everyone's all-time favorite, completing the square. And of course, the second method will be by the approach of finding our x-intercepts. Okay, with the x-intercepts, and then you find the line of symmetry. From the line of symmetry, it gives you the coordinates of this minimum point. Okay, but in AMAS, I've actually briefly mentioned before, in AMAS, what is amazing here is you can actually make use of dy dx as well. So please bear in mind, as we went through earlier just now, one of the examples for a stationary point is a minimum point. So our minimum point here is also a stationary point. And what do we know? At stationary point, my dy dx is equals to 0. All right, so what we need to do here is, first up, again, let's go and find dy dx, which gives us 2x minus 7. Okay, then at stationary point, dy dx is equals to 0. So I shall equate my dy dx here equals to 0. And you'll be able to find that the x value here is 7 over 2. But we are not done with the question. We are supposed to find the coordinates. So at x equals to 7 over 2, what is my y value? Just sub into this equation over here, x squared minus 7x plus 2. You should get negative 10 and 1/4. So ladies and gentlemen, this is the coordinates of the turning point here, which is a minimum point. Okay, so can I invite the relief teacher to pause this video for a short while so that our students can catch up with what has been gone through. Thank you. All right, so ladies and gentlemen, before I continue, actually the question that I have for all of us here is this: do all curves have only one stationary point? I mean, because based on the past two examples that we went through, the first example we only have one coordinate where stationary point is equals to where we only have one stationary point. In example two, again, we also have only one stationary point. So that begs the question: do all curves only have one stationary point? Well, the truth is, I think some of us may know the answer to this is no, because we can have a case where I can have a curve like this. All right, mind you, this is a typical example of a cubic curve as well. Yeah, this can be a cubic curve where actually I have two stationary points here, where my dy dx equals to 0. Okay, likewise, if you go on to a higher level, next time in JC, you may even come across a curve like this. Okay, where you have point of inflection here, a maximum point, a minimum point, and a maximum point again. So you realize over here there are, oops, sorry, we have 4 stationary points here. Okay, so do all curves have only one stationary point? Of course, our answer here is no. Okay, so next up we are going to be discussing on a curve where we have more than one stationary point, as you would see. All right, so ladies and gentlemen, we have this question here. Now, not to worry, you don't have to hurriedly jot this question down. I'll give you guys some time to copy this down later. So this is a question: given y equals to 2x cubed minus 9x squared plus 12x minus 4, determine the coordinates of the stationary points of the curve. All right, so what should we do? I'm not going to show you guys the answer now, but I'll let you guys to try on your own. Let us walk through the process again. If we talk about stationary points, we are talking about the case where dy over dx will be equals to 0. So ladies and gentlemen, first up, you're going to need to go and find out what is dy over dx first. And of course, next you got to solve the equation where dy over dx equals to 0. That will give you the x coordinate. Okay, that will only give you half the answer because we're talking about coordinates. And last but not least, you need to sub the x value into, okay, sub the x value. Sometimes you may have more than one possible answer into the original equation, sub into y to find the corresponding y values as well. Then you will have the set of coordinates where dy dx is equals to 0. All right, I'll let you guys to try this question now. I believe you guys should be able to complete this within 5 minutes or less. So can I invite the relief teacher to pause this video and allow you guys some time to try this. Your 5 minutes starts now. All right, so ladies and gentlemen, I believe you should be done with the question. Okay, so first up, this is what we need to do. We need to go and find out what is dy dx. Now, as I go through, please mark your work as well. Okay, so once I found dy dx, and take note at stationary point, our dy dx will be equals to 0. This is when you attempt to solve your quadratic equation. And you should end up with these two sets of values here, x equals to 1 or x equals to 2. But not to forget, this is only our x coordinate. We also need to go and find out what is the y coordinate. So at x equals to 1, sub this back into our original equation. You should get y equals to 1 as well. So ladies and gentlemen, we have our first set of coordinates, 1, 1. Now, not to forget, at x equals to 2, again, sub it back into original equation. You should get y equals to 0. And this is another set of coordinates to 0. All right, so ladies and gentlemen, these are the two sets of coordinates where we have the stationary points of the curve. But before I continue, this is my question to everyone here. Now, as we know, stationary points, okay, a stationary point can either be a minimum, a maximum, or a point of inflection. But the question is this: does these two sets of coordinates here give us any detail on whether this point is a minimum point, a maximum point, or a point of inflection? Well, it doesn't, right? Obviously, it only tells you that at these 2 points, my dy dx is equals to 0. So this is when I'm going to walk you guys through one of the tests on testing the nature of the turning point. All right, so ladies and gentlemen, please take note of the new question, part B, a continuation from part A. A typical question that we'd like to ask is this: determine the nature of this point. So what do we mean by nature? Mother nature, what kind of nature? Okay, when we talk about nature of the points, we are asking to determine whether the point is a minimum point, a maximum point, or a point of inflection. Okay, so this is where I'm gonna introduce to you guys this amazing test. We call it, well, math people are very boring. Just call this the first derivative test. Nothing fanciful, no fancy names to it. Okay, notice here I mentioned something called construct the table. Yes, for our first derivative test, we are expected to construct a table, and we are going to make use of certain trends, or rather certain shapes of the tangent line, which we'll find out in a while, to help us determine the shape of this turning point. So what exactly am I talking about here? So ladies and gentlemen, let us focus on this first set of stationary points. So this is the table I'm going to construct. So I'm going to have x, I'm going to have dy over dx, and I'm going to have this thing called a tangent line. Now, this should form me three categories here, all right? All right, so this is the table that you should have, 3 rows and 3 columns over here. Okay, so what are values that I'm going to use? This first row over here is the x value, which I'm going to substitute into dy dx. So of course, we have x equals to 1, because at x equals to 1, I have my stationary point. That is why I'm going to introduce to you guys this thing here, 1 minus and 1 plus. So what does 1 minus and 1 plus here actually mean? Okay, just a very simple thing. 1 plus, for example, is a value very close to 1 but greater than 1. So for example, I'm talking about a value that is 1.01. And similarly over here is a value that is very close to 1. Minus means it will be smaller than 1. So I'm looking at a value of, for example, 0.99. All right, so you guys might be wondering, why am I considering 1.01 and 0.9, and what am I going to do with these values here? Well, what I'm going to do is I'm going to substitute these values into dy dx. All right, remember what our dy dx is? In case you guys forgot or you guys did not manage to jot down, our dy dx is 6x squared minus 18x plus 12. This is the dy dx where we're going to substitute our values into it. Okay, so first up, very simple. Let's sub x equals to 1 into our dy dx. Don't have to calculate because we know for sure that dy dx where x equals to 1 will be equals to 0. Now, how about 1 plus? That means when I substitute 1.01 into dy dx. Okay, I'll allow you guys a quick 15 seconds. Key this into your calculator. Sub in x equals to 1.01 into dy dx. And let's see what you get. Your 15 seconds starts now. 1,000, 9,000, 10,000, 11,000, 12,000, 13,000, 14,000, 15,000. Yes, if you have substituted 1.01 into dy dx, you notice that the calculator actually gives you a negative value. Now, you don't have to write down what exactly this value is, just have to indicate here that it's negative. Similarly, sub x equals to 0.99 into my dy dx, and what do you get? I'll give you guys another quick 15 seconds. Relief teacher, can you please pause the video, give them a 15 seconds to try this out now? Thank you. Okay, I believe you guys should have calculated and you should be getting a pretty small positive answer. Again, you don't have to write down the exact value, but you just have to write it as positive. Okay, so how would our tangent line look like when I have a positive dy dx? Now that means our tangent line should be going up slope. Now at x equals to 1, I have dy dx equals to 0. That means my tangent line is a horizontal line. And last but not least, when I have an x value that is slightly greater than 1, I have a negative gradient. Dy dx is negative. That means to say this is my negative gradient tangent line. And what do you realize? Overall, what is the shape? Notice, I'm going to add in the last column over, the last row over here. Based on these tangent lines, I am going to form this shape over here. Okay, just to show everyone, this is the shape that I will get. So ladies and gentlemen, so therefore at 1, 1 by the first derivative test, we have a maximum point. All right, so in similar fashion, let us apply it on the next set of coordinates that is 2, 0. All right, so ladies and gentlemen, for the next set of point 2, 0, you should have constructed a table like this. Okay, so just to re-emphasize again, when I talk about 2 plus, I'm talking about a value that is really close to 2. But bigger than 2 here, so I'm looking at 2.01, and likewise over here I'm looking at 1.99. All right, so let's start off with the more straightforward one. If I sub x equals to 2 into my dy dx, I'm definitely going to get 0. There's no need for us to compute here. Okay, and of course when I have dy dx equals to 0, I'm looking at a horizontal line. But what happens when I sub 2.01 into my dy dx? Now this is when I need you guys to use your calculator and calculate this now. Give you guys a quick 10 seconds to do so. All right, so if you guys have substituted correctly and pressed into a calculator correctly, you should have gotten a positive answer, and that would mean that we have a positive gradient, positive tangent line. Okay, how about 1.99? Can you guys start working on this? Sub 1.99 into dy dx, and what do you get? Okay, you guys will realize that you actually get a negative answer, and therefore the shape of a tangent line will be as such. And therefore, overall, the shape based on my tangent lines formed here, I should be getting a shape of the curve like this, which is actually a minimum point. So ladies and gentlemen, at 2, 0, the nature of my turning point is actually sorry, not a maximum, but rather a minimum point here. And so there you have it. What I've just done is to use the first derivative test where I constructed the table, making use of the shape of our tangent lines to help us determine the nature of the turning points of our stationary points here. All right, so before I get you guys to try the next example, just a very quick recap. So first of all, when we want to test out, or rather when we want to go and find out what is the stationary point, first of all, the first thing is we go and find dy over dx. Now that's the first thing we do. And second thing, to find the coordinates of the stationary point, we solve dy dx equals to 0, where I get the x coordinates. And to complete our answer, we sub the x value into the original equation that's given to me, and that should give us a set of coordinates, sometimes more than one possible set of coordinates here. Okay, and what we just went through is the first derivative test. And the purpose of this test is to help us find out the nature of the turning point. Okay, where you're supposed to identify whether it's a maximum point, a minimum point, or a point of inflection. All right, so ladies and gentlemen, with that knowledge in mind, especially on how to construct the table for our first derivative test. I will let you guys now to go to your textbook, turn to page 404. I would like you guys to look at try 4. Okay, can the relief teacher please pause the video in just a while, allow our students about uh, 7 minutes to try this question now. Thank you. All right, I suppose you guys have completed the question, so let us go through the answer now. Now, as I go through, please mark your work with a pencil as well. So, first of all, you're supposed to go and find out what is dy dx. So, very straightforward. Okay, apply your chain rule, and you guys should get 6x squared times x cubed minus 1. And for part 2, to find the nature of the stationary points. First of all, we of course need to go and determine what are the coordinates of our stationary points first. Okay, so equate our dy dx to 0, solve the equation. You should get x equals to 0 or x equals to 1. But that we have not completed the question yet. We are supposed to find the coordinates. Sub x equals to 0 into y. Please take note, some of you might actually sub back into our dy dx. So please a note to yourself is sub into y, not dy dx. That's the tendency that many of us may actually make. Okay, that's a mistake that many of us tend to make. Okay, so ladies and gentlemen, these are your two stationary points. They are 0, -2, and 1, -3. Now, at this juncture, I only know that they are the stationary points, but I do not know the nature of these turning points. So I hope you guys have applied the first derivative test correctly. All right, so if you have applied your first derivative test by constructing the table at x equals to 0, this is the table that we should have. So in case some of us are still not quite clear about the x value I should sub in, okay, number that is very close to 0 but slightly more than 0, we can talk about 0.01. And number that is very close to 0 but less than 0, we can talk about negative 0.01. Yep. So sub these values into your dy dx to determine whether it's a positive or a negative value over here. Okay, sorry, there's a mistake here. This should be negative as well. Okay, so ladies and gentlemen, you'll notice that at x equals to 0, I actually have this shape over here, which means I neither have a maximum point, not a minimum point as well. It is actually a point of inflection. All right, a point of inflection can either look like this or like this. Basically, it's clearly not a maximum or a minimum point. All right, so for the second point, 1, -3 at x equals to 1, my dy dx will be 0. That explains a horizontal tangent line. At 1 plus, when looking at 1.01 sub into dy dx, you should get a positive value and of course a positive gradient. For 1 minus, well, we're looking at 0.99. Yeah, sub into dy dx, you should get a negative value and a negative gradient over here. And therefore, the shape in this case should be a minimum point. So therefore, at 1, -3, ladies and gentlemen, we actually have a minimum point. I hope you guys have this. All right, so some of you at this juncture may still have this question. So if I talk about, the value that is plus and minus, what is the range I should use? Okay, you realize the examples that I've quoted, we usually use a plus minus of 0.01. Now we want to make sure that the value that we sub into dy dx is as close to the x value of the stationary point as possible. Okay, so a guideline is this: the value that you want to sub into dy dx. Well, when using the first derivative test, the range give it a plus minus 0.01. All right. Okay, so ladies and gentlemen, with that, we are done with the first derivative test. Now, for some of us, You might be wondering, you know, if I were to call this a first derivative test, does that mean that I actually have a second derivative test? Yes, we do, unfortunately. Okay, now this may come as a comfort for some of us because I think some of us may find that the first derivative test, you know, having to construct a table might be a bit too troublesome. So this is where I'm going to introduce to you guys the second derivative test. Okay, now for the second derivative test, you don't have to construct the table, but what is the extra thing that you need to do? Second derivative test is when we need to differentiate with respect to x, our dear dy dx. Okay, that means to say I need to differentiate my dy dx, which will give us the d2y over dx squared. Yes, this is something that something new that you guys are going to learn today. This new symbol over here, d2y over dx squared. Okay, that is our second derivative test. Okay, so we shall now attempt to apply this concept on one of the earlier examples that we have tried. Now, which example am I talking about? I'll let you guys refer to example number 3, where I gave you guys this equation: y equals to 2x cubed minus 9x squared plus 12x minus 4. Yes, if you guys can recall from the earlier example, this is what we did. Our stationary points were actually 1, 1, and 2, 0. Yes, these were the two stationary points that we found from the previous examples. And we even had the nature of these stationary points, okay? For 1, 1, we found using the first derivative test that it was a maximum point, and that for 2, 0, it was a minimum point. Now, ladies and gentlemen, at this juncture, I would like you to presume that, we do not know the answer. Okay, just presume that we do not know the answer. Presume we didn't know this. Okay, now we shall now attempt to use our second derivative test to solve this question. So, what is the nature of the turning point? Okay, that is the main question. The nature of the stationary point. Okay, so ladies and gentlemen, as I mentioned, first of all, we got to go and find out what is our dy dx, which we have found earlier to be 6x squared minus 18x plus 12. Okay, and you haven't gotten dy to solve this equation. Okay, just to skip everyone the hassle, if you have solved it, this is how it should be. You have x equals to 1 or x equals to 2. Now, with the second derivative test, all right, we need to go and find out what is d2y over dx squared. Okay, that means to say I need to further differentiate my dy dx, which in this case, okay, for a head start, you can write this down. Okay, it's very easy. You notice that this is just 12x minus 18. So what do I do next? Okay, the next part I'll do is I will sub the x value of stationary point into my d2y over dx squared. And ladies and gentlemen, when I sub x equals to 1 into my d2y over dx squared, you'll notice that I actually have 12 times 1 minus 18. That gives us a negative 6, which is less than 0. So what does that mean when I have a d2y over dx squared with a value of negative 6, which is less than 0? So please jot this down. For d2y dx squared less than 0, I would actually have a maximum point. And that would coincide with the earlier example, the first derivative test. Using the first derivative test, you'll notice that, hey, okay, that gives me a maximum point. All right, so can the relief teacher please pause this video for now to allow the students to have some time to jot this down. All right, I just did a bit of a rearrangement here. So ladies and gentlemen, please take note, where my d2y over dx squared is less than 0, we would have a maximum point. So now let's have a look at x equals to 2, because that is our second stationary point here. Okay, what will my d2y over dx squared be equals to? Sub x equals to 2 into my d2y over dx squared, which is 12 times 2 minus 18, sorry, 12 times 2 squared minus 18, and that should give me a 12, which you realize is greater than 0. And ladies and gentlemen, please take note, when the value of d2y over dx squared is greater than 0, I would have a minimum point. So therefore, at 2, 0, we have a minimum point. Okay, so let us attempt to apply the second derivative test on another example that we have tried earlier. I would like you guys to have a look at try 4. Again, back to try 4. So instead of applying the first derivative test, I would like you guys to try to apply the second derivative test. Okay, in case some of us still can't quite follow, so always remember, I need to go and find out what is my dy dx, and then I need to solve my equation dy dx equals to 0 to get the x value of my stationary point. And then number 3, I need to sub x value into my original equation in order to get my coordinates. And then number 4, I need to apply my first or second derivative test to determine the nature of turning point. Okay, so these are the steps to follow. And as we just went through the second derivative test, what do we need to do when applying the second derivative test? We need to go and find out what is d2y over dx squared, which is simply a differentiation with respect to x, our dy dx. Then I need to sub in the x value of our stationary point, which I've just shown you earlier on, into my d2y over dx squared. And I also went through with you guys, if d2y over dx squared is greater than 0, that should give us a minimum point. If my d2y over dx squared is less than 0, that should give us a maximum point. Now at this juncture, some of us might be thinking, what about d2y over dx squared equals to 0? What happens then? Okay, I shan't reveal the secret to you guys, but I'll let you guys to apply the second derivative test on try 4 of our textbook. Can you guys please kindly go and try them now and give you guys a quick 5 minutes to do that. Thank you. All right, so I hope you guys have applied the second derivative test on try 4. Okay, so some of you might have applied a product rule in the differentiation of dy dx, but actually what I would prefer to do is I would like to expand them first. Okay, because this is quite an easy expansion, and from there I just apply my power rule. Differentiate term by term, my d2y over dx squared should be 30x4 minus 12x. Now, not to worry, if you use product rule, we should end up with the same answer actually. So based on our earlier attempt, our stationary points are 0, -2, and 1, -3. So at x equals to 0, if I sub into my d2y over dx squared, I will get 0. Now at this juncture, some of you may be quick to guess that it's a point of inflection. Well, in fact, if I found earlier, yes, indeed, using the first derivative test, it is a point of inflection, but more on this in a while actually. I'm going to talk more about this later, but let's move on to x equals to 1. When I sub into d2y over dx squared, you'll notice I actually get something that's greater than 0. That means to say it is a minimum point. Now, ladies and gentlemen, let's come back to here. This, when my d2y over dx squared is equals to 0, to be honest, there is no conclusion. Okay, I cannot conclude whether it's a point of inflection, whether it's a maximum point, or whether it's a minimum point. Now, some of you might be thinking, hey, if I use first derivative test over here in the earlier example, indeed I get a point of inflection. So since this is equals to 0, shouldn't I get a point of inflection? Well, I'll let you guys to try the next example. Okay, so people, let's move on to the next example. Example number 5. Okay, now here's the question. All right, so people, this is the example given y equals to x to the power of 4. Find the coordinates of the stationary point and the nature of the turning point. Now, at this juncture, I'm going to divide the class into two halves. Now, first half, I am looking at the first 4 rows. That means from Xiangming's row all the way to where, if I can recall, where Gerald is seated. Okay, so this first 4 rows, you guys would attempt to solve this question by, sorry about that. Now this first half of the class, you guys will attempt to solve this question by the first derivative test method. Okay, and the second half, that means to say I'm looking at the row from Rachel all the way to Dave. Okay, right, so the next half of the class, you guys will attempt to do this question by the second derivative test method. Okay, so I'll give you guys about, this is quite a straightforward task, about 5 minutes, right? Relief teacher, can you please allow the class 5 minutes to try this question, and the time starts now. All right, so I guess you guys should have tried the question. And what I've done over here is I've written down the steps that you guys would have done. Now, the first part is a pretty standard thing. All of us, be it the first half or the second half of the class, you should have done this. When find dy dx, which is 4x cubed, equate it to 0 to find the x value. And then after that, sub x equals to 0 into y to find the coordinates. So you should have this set of coordinates, which is your stationary point. Okay, so first half of the class, who tried the first derivative test method. Okay, hope you guys find this familiar. Construct the table, 0 plus, 0 minus, sub into dy dx. This is what you should get, and you notice that you actually get a minimum point by the first derivative test method. But if you have to go on by the second derivative test, which is what the second half of the class did, you would have gone on to find d2y over dx squared, which is 12x squared. You sub x equals to 0. And you realize that is actually equals to 0. So does that mean it's a point of inflection? So notice that these two approaches here gives us two different answers. I think the graph itself speaks the best. So actually, if you don't believe me, go back this evening, go and Google search how a y equals to x4 graph look like. But I can tell you for sure, this is how the graph looks like. In fact, you would have learned this in e-math as well. This is how the graph looks like. Y equals to x power 4, which actually looks pretty much like a quadratic curve. So ladies and gentlemen, you notice it cuts through the origin, and at the origin it is actually a minimum point. That means that our first derivative test is actually right. Okay, so the point that I'm trying to get you guys to realize is this, which is also a limitation of the second derivative test. Okay, when I have d2y over dx squared equals to 0, we cannot conclude whether it is a point of inflection, whether it's a maximum point or minimum point. So please bear in mind, when you have d2y over dx squared equals to 0, it is inconclusive. Then what happens? And what must I do? Then I revert to my first derivative test method. All right, so ladies and gentlemen, please bear this in mind. If you were to use d2y over dx squared and you realize that the value is equals to 0, no choice, we got to suck thumb and go back to using the first derivative test to help us determine whether it's a maximum point, a minimum point, or a point of inflection. All right, ladies and gentlemen, so just a very quick summary. Okay, so far today, what we have learned is we have learned the first derivative test and the second derivative test method. Okay, but of course, the main important thing I think I mentioned before, always go and find out what is dy dx. Second thing, we always gotta equate dy dx equals to 0 to find our x value. And number 3, we need to sub the x value into y to find the coordinates. And number 4, we need to apply either the first derivative test method, where I need to construct table, make use of the shape of the slopes of the tangent, which will determine the nature of the turning point. Of course, then you have the second derivative test method. Sorry. Second derivative test method, where you need to go and find out what is your d2y over dx squared, and you sub your x value into your d2y over dx squared to determine. And like I've mentioned earlier on, if d2y over dx squared is greater than 0, we have a minimum point. d2y over dx squared is less than 0, we have a maximum point. And if my d2y over dx squared is equals to 0, it is inconclusive. And if this is the case, we need to revert back, okay, to my first derivative test to help us determine whether it's a maximum point or minimum point or a point of inflection. All right, so thank you so much, ladies and gentlemen, for paying such close attention to the video, I hope. What I'll like you guys to do is this. All right, so this is basically the summary of everything. Now, at this point in time, can I invite the relief teacher to pause this video to allow some of our students who will like to take down the summary of what we have went through today. I give you guys about a quick 2 minutes to jot this down. All right, so ladies and gentlemen, I hope you have consolidated what I've learned today. And of course, with that, I would like you guys to make use of the remaining time that you have in class to complete the following question. Try 7, which is found on page 408. And of course, exercise 16.1. Question 5. If I read question 5 carefully, you're supposed to use the first derivative test method. Question 6b, which will require you to use the second derivative test method. And also question 13 and question 14, which are all application questions. Now, I'd like you guys to try all these questions on the foolscap paper. All right. Please make full use of the remaining time that you have to try these questions. And if you can't finish it, it's okay. Bring back, finish it, and submit to CANES on the 20th of February. Okay, so you realize it's actually the next day. You don't have much time, so please make full use of the time that you have now to complete the work. I'll see you guys soon. Thank you, and have a good day. And thank you to the relief teacher as well. Thank you so much. Bye bye.